Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 4. Stationary Iterative Methods, Convergence Issues and Convergence Rate. For the formal theory of the stationary iterative methods, we will decompose the coefficient matrix as follows. Where D, U, and L are diagonal, upper, and lower triangular matrices, respectively. However, the L and U notations denote the lower and upper triangular matrices, whose primary diagonal elements are 0. They should not be confused with those matrix definitions as in the LU decomposition methods. We start with the Jacobi method. The diagonal elements are isolated in matrix form as follows. Now we introduce superscript notation. We keep the prior estimates on the right-hand side and the current estimate on the left-hand side. Solving for the current estimate gives the following expression. Also recall that inverting a diagonal matrix is simply inverting the diagonal elements. Here matrix M sub J is referred to as the Jacobi iteration matrix. The Gauss-Seidel iteration procedure can be expressed in matrix form as follows. The matrix product Lx is calculated using the current estimates of x. Solving this equation for the current estimate yields the following. Here M sub Gs is the Gauss-Seidel iteration matrix, and D minus L is a lower triangular matrix. Skipping the lengthy procedure, the SOR iteration equations are expressed as follows. Where M sub omega is the SOR iteration matrix, which takes the following form. Where omega is the relaxation parameter. To generalize the convergence properties of iterative methods, consider the following iteration equations in fixed-point matrix form, where M is the iteration matrix and C is a vector. Then, any iteration scheme can be expressed as follows. Subtracting the two equations side by side gives the following matrix equation for the true error. Note that the true error at any iteration level depends on the prior true error via the iteration matrix. Employing this relationship successively, the error at the pth iteration step becomes. For an arbitrary initial guess, x0 or e0, the sequence of estimates should converge to x as p goes to infinity if the true error goes to 0 for increasing iterations. Hence, in order for an iterative algorithm to converge for any arbitrary initial guess vector, the necessary and sufficient condition is that the pth power of M should yield 0 matrix. It can be shown that the true error is proportional to the product of the pth power of the largest eigenvalue and its associated eigenvector. For the proof, see section 3.3 of the textbook. Taking the L2 norm of both sides, we find ρm denotes the spectral radius of the iteration matrix M, and it must be less than 1 so that the error decays as p increases. Otherwise, the iterative method will grow unboundedly and diverge. That is, for Jacobi or Gauss-Seidel iteration matrices, the upper bound for the spectral radii is 1. Computing the spectral radius can be very expensive and time-consuming. Instead, we can estimate it using the Gershgorin theorem in terms of the original coefficient matrix, which follows. The diagonal dominance of a coefficient matrix A is a sufficient condition for convergence. That is, a matrix A is said to be strictly diagonally dominant if, for every row, the absolute value of the diagonal element is greater than the sum of the absolute values of all the other non-diagonal elements in that row. It is said to be weakly diagonally dominant if, for each row, the absolute value of the diagonal element is greater than or equal to the sum of the absolute values of the other non-diagonal elements in that row. If A is a diagonally dominant coefficient matrix, then the Jacobi or Gauss-Seidel methods do converge for any initial guess vector x0. However, there are cases where Jacobi, Gauss-Seidel, or both methods may converge to an approximate solution even if A does not meet the sufficient condition. For a sufficiently large number of iterations and asymptotic convergence rate, the 1/a ratio gives approximately the number of iterations needed to reduce the error by a factor of 10. The smaller the spectral radius is, the larger the convergence rate becomes. The number of iterations to reduce the error by more than an order of magnitude is found by 1/r. The speed at which a sequence of estimates approaches its limit is called the rate of convergence. A faster rate indicates that fewer iterations are required to obtain a reasonably accurate estimate. Mathematically speaking, the rate of convergence of the iterative scheme is defined by the following logarithmic expression, where the log function is the 10-based logarithm. The minimum number of iterations required to obtain a solution within epsilon equals 10 to the minus m can be estimated as follows. There is a quadratic relationship between the spectral radii of the Jacobi and the SOR iteration matrices, where ρmj and ρm are the spectral radii of Jacobi and SOR matrices. Solving the quadratic equation for ρm yields the following solution, where omega optimum is the optimum relaxation or acceleration parameter. We note that, in certain cases, the spectral radius of the Gauss-Seidel iteration matrix becomes the square of the spectral radius of the Jacobi iteration matrix. In other words, this relationship typically holds under certain conditions, such as when the system is either positive definite or the eigenvalues of the Jacobi iteration matrix lambda correspond to the squares of the eigenvalues of the Gauss-Seidel iteration matrix mu. In such cases, the optimum relaxation parameter can be estimated by the following formulas. The variation of SOR spectral radius as a function of omega and spectral radius of the Jacobi iteration matrix for a positive definite system is given below. The spectral radius decreases as omega increases from 1 up to a certain value. Beyond a certain point, the spectral radius starts to increase again, meaning that the method is no longer improving convergence and may even become unstable. When the spectral radius of the Jacobi iteration matrix approaches towards 0, the spectral radius of the SOR iteration matrix also approaches towards 0, meaning that the convergence property of the system improves further. Consider solving the following 3x3 system of linear equations. Using the theoretical analysis, we will determine the spectral radius and convergence rates of the Jacobi, Gauss-Seidel, and SOR iteration matrices. First, we will split the coefficient matrix as follows. The Jacobi iteration matrix is constructed as follows. The eigenvalues of the Jacobi iteration matrix are obtained as follows. The maximum magnitude eigenvalue gives the spectral radius of mj as 0.8431. The convergence rate of the Jacobi iterations is found to be 0.07412. An estimate for the number of iterations within epsilon equals 10 to minus 4 can be found as 54, which is pretty close to 57 iterations that was obtained in video 2. The Gauss-Seidel iteration matrix is constructed as follows. The eigenvalues of the Gauss-Seidel iteration matrix are obtained as follows. The maximum magnitude eigenvalue gives the spectral radius of MGS as 0.3883. The convergence rate of the Gauss-Seidel iterations is found to be 0.4108. An estimate for the number of iterations within epsilon equals 10 to minus 4 can be found as 10, which is also close to the value of 13 obtained in video 3. Notice that in this example, the quadratic relation between the spectral radii does not hold. Yet we will estimate the optimum relaxation parameter using the follow expression, which yields the value of 1.3. The spectral radius of the SOR iterations for the omega optimum is found to be 0.3, and the convergence rate is calculated to be 0.5229. An estimate for the number of iterations becomes 8. Using an SOR code, the system is solved for varying relaxation parameter values. A plot depicting the variation of the number of iterations with the relaxation parameter is depicted in the figure below. Note that the optimum value is obtained for omega equals 1.2 with 8 iterations, while for omega equals 1.3 the estimates converged in 10 iterations. Omega optimum is a bit off, because matrix A is not positive definite. That is all for now. See you next time with another topic. Bye.